event. Okay, with networking. And as we started recording, let's do this again. Welcome everybody to the TAPAS Training Event 6. This is not an error in the matrix, and we are at industry targeted event with networking. So welcome virtually in Augsburg, in Germany, in the south of Germany, in Bavaria. In Upper Bavaria, no, sorry, in Schwaben, actually. I am from Upper Bavaria, so pardon this confusion. You're in Schwaben, the very nicely countryside shaped region, which you're missing if you're not in Augsburg now, as some of you are, which is a pity, but we hope to see you all in Augsburg at some other point, and you will at least virtually see it during this event. Let me introduce first maybe Zhao Shen and Katrin Bartel-Poconi, who are largely running this event. Zhao and Katrin, can you quickly say hi maybe?
Hello, everyone. Yeah,
Thanks a million to them. They put this all together and they will also be guiding you through these days. So we will be having today, tomorrow, and then 30 June prepared for you with a lot of exciting stuff. And let me just first welcome you at our chair. So you're at the University of Augsburg, which is a young university. We just passed our 50s. And despite we are located at the old University of Augsburg campus site, this is just 50 plus years old. Our chair is roughly turning 5 soon, so it's also rather new, and we are the chair of embedded intelligence for healthcare and well-being. This doesn't sound so speech, but it sounds pathology a lot. But we're largely doing speech, to be honest. Lately, we've been doing a lot on COVID-19 recognition from the voice, and we're recognizing depression and burnout and autism and whatnots from the voice. So we're really largely doing, in fact, speech and health things. You may know from our team some things we do together with Erlangen, for example, we're running, and others we're running since more than a decade, the Interspeech Computational Paralinguistics Challenge, or COMPARE for short. Maybe some of you have been using OpenSmile, a toolkit which originally comes from the team, which has then been moving from Munich over Passau to Augsburg, where we are now. The Open Crossbow toolkit, I Hear You Play, and others, and most lately, or most recently, the Enhance speech enhancement toolkit, all of which you can find on GitHub. At this moment, we're also co-organizing here, which is a Europe challenge you might want to find interest in, on holistic evaluation of audio representations. And with that, let's go into this actual event. So my name is Björn Schuller. I'm the chair here in Augsburg, and this is why I have the honor to give you this welcome speech. But afterwards, as I said, I will put you into the much better prepared hands of Zhao and Katrin. Next, we will have Andreas, and Andreas is also visible already. Andreas, say hi.
Hi, everybody.
We will be talking about digital health in the wild. Andreas is with Audiering, but he's also with the University of Augsburg. So here is an example of somebody doing his PhD externally from working in the industry side. And then we will have a first virtual coffee break, a discussion round in which we want you to talk in groups about topics we have prepared for you. And Zhao and Katrin will say a few words on that. And then we will have, after the lunch break, your presentations. If you're an ESR. Tomorrow we will start with another exciting guest, Volker Fischer from EML Speech Technology GmbH, which is a German form of company. Research and development at EML Speech Technologies. Then we will have Felix Burkhardt. He's at Audiering, looking over the projects on highest levels and looking over scientific coordination also. But he's also a professor at the Technical University of Berlin. So this is maybe an interesting case of being both an academic and an industrial, like myself, who co-founded Audiering. Emotional voices in human-computer interaction. And Felix is known since many decades for working on emotion and voices. I actually took inspiration from his PhD thesis when I wrote mine about emotion and voice. So a very recommended piece of work and a super interesting speaker also. After lunch break, we will then have Florian Eiben, the CTO, Chief Technology Officer of Audeering, talking about OpenSmile, which I said some of you may know, and AI Sound Lab. So Audeering's tools for voice research, which is quite interesting because I hope Florian will also be talking about how to go from being an academic, doing something open source, into moving into building a company around that and yeah, making it somehow commercially exploitable. After virtual coffee break, we will be having your presentations and feedback on the discussion round. And then this virtual city tour through Augsburg, we really wish you would have been here and enjoyed maybe some Maultaschen, some plum cake, for which Augsburg is very famous, and some Spezi, which was founded in Augsburg, is very popular. It's a mix of Coke and orange lemonade, also known in other parts of the world, of course, under other names, but in Germany it's known as Spezi and comes from Augsburg. But the virtual one will be fun, I'm sure, and that's how we do it these days. And then we'll have a little break for you of some days, but we hope to see you all back on 30 June, starting with a Gather Town meeting. And then we will have Chu Cheng Kong from ByteDance talking about AI for sound, large-scale audio tagging with deep neural networks, and Tanvina Patel from Cognate Semantics talking about semi-supervised learning for speech recognition in Indian languages. So 2 more exciting guests from the industry talking about research in the industry and how it's done there. And then we will have another round of ESR presentations. Before, you will sadly have to see me again, sadly, of course, because it will be the end of this exciting event. And with that, I will largely go back to Zhao and Katrin, who you can reach under our email addresses here. They put their long ones here. We are, however, also reachable under @uni-a.de. So that should also arrive with the same first name, last name pattern. And maybe this is where I hand over to Zhao to explain a little bit on the particular events. Zhao, just say skip forward if you need the next slide or something light. This is a speech event, so you can use voice control.
Yeah, this will be our virtual coffee breaks rooms links, and we will have 2 kinds of links: business coffee break and the scientific coffee break. No matter which one you are interested in, you can just move in. Yeah.
False recognition. Sorry.
You can also switch between the 2 rooms. And then this will be the ESR discussions. In this morning, we will introduce this later again about it. Yeah, we will. These are the ESR discussions. We have already prepared 4 topics. In the second session in this morning, we will discuss about them. Yeah. And afterwards, this will be an exciting virtual city tour tomorrow afternoon. Yeah, let's look forward what we will see tomorrow.
Oops. My bad. Okay. And the link to the Gather Town meeting. And that's about it, right? So welcome again to Augsburg. Welcome to our chair, and please, of course, also feel free to drop me emails at any moment in time, which is simply schuller@uni-a.de again. So you can, Björn Schuller, sorry, björn.schuller@uni-a.de. And Katrin, Zhao, please, I trust in your excellent guidance from now on. Thank you very, very much.
Thank you very much. So welcome also from my side for those of you who do not know me yet. So my name is Katrin Bartol-Bokorny. I'm a postdoc at Björn's chair, and I'm very much looking forward to all the talks and discussions we've prepared. Yeah, and so let me now come to the first talk or the first speaker. So Andreas Triantaviopoulos, welcome. Welcome here to this training event. Yeah, Andreas is, as we already heard, an AI researcher at Audiering and also doing his PhD at the University of Augsburg. His main research fields lie in speech emotion recognition and multimodal information fusion. And he will now give us a talk on digital health in the wild. So welcome, Andreas. We are very much looking forward to your talk.
Thank you, Catherine. Can you see my screen now? Yeah. Okay.
Yes, we can.
Yep.
So thanks for pronouncing my name almost correctly. You know, you got it very well. Congratulations on that. Most people have problems with it. So I'm going to be talking about digital health in the wild. You already heard from Björn and Catherine that I'm working as an AI researcher at Audiering for almost 3 years now. And I'm also a doctoral candidate at the TAPAS. So, you know, I'm stuck in the limbo between academia and industry and looking at both worlds. I have mostly been working in speech and motion recognition, but I've also done digital health work as part of my work at Audiering mainly. A few words about Audiering. It was founded in 2012 as a spin-off from the University of Munich, Technical University of Munich. Now we're almost at 70 people, last time I heard. And we're located in Munich, Berlin, and also a few people working remotely. Actually, more of us working remotely now due to the coronavirus. We're mostly focused on speech analysis and emotion recognition, and that's where we started. But as I said, we're also doing digital health projects. You'll hear more about that, I guess, from our CDO, Florian Eiben, tomorrow, so I will not talk more about that right now. Instead, I'm going to move into my talk today. So, you know, I'm assuming that, well, not I'm assuming, I'm sure that all of you know what digital health and voice are. You know, you know that there's several things that are impacting voice. Most notably, or, you know, COVID-19 is, of course, the epicenter right now of attention and respiratory diseases in general. But I guess all of you, or many of you, have done work in other things like Parkinson's or Alzheimer's, or diseases that people have been studying for a longer time and looking for their impacts on voice. Since I'm sure you guys know a lot about this, I'm not going to expand on it further. Instead, I'm going to try to talk about the difference between digital health in the lab and digital health in the wild, which is the topic of this talk. What I consider to be digital health in the lab is something where you're iterating over the following thing. You start with a database, you prepare the database in a way that you can process it, that might be standard data science, cleaning stuff, and so on. Then you work on modeling, and modeling could be machine learning modeling in the sense that you're trying to predict something, or it could be that you're trying to understand something. And this results in a scientific study. You know, you publish it, you learn from it, or you learn from the studies of others, and you iterate over your process. That's obviously an oversimplification, right? But you guys know what I mean. You guys have been doing that for years now, since you're researchers yourselves. The contrast with in the wild is you have a similar picture, but I tried to distill in that picture that you're working as part of a team. You're working, in my case, I'm working for a small to medium-sized company, you know, Audiering. We have our own core expertise, we have what we bring to the table, and we're communicating with other people. You know, those could be clients, other companies, those could be medical organizations, doctors, patients. And those are the people who come in the picture later as I go through the talk. What we're doing is also a version of what's happening in the lab. You know, we're setting the scene in the sense that we're deciding what problem we have to solve. We then have to work to get the data to solve that problem. You know, we have to actually solve that problem or try to solve that problem. And in the process, we learn something and we iterate on that and try to build something that's useful in the real world. That's the goal, right? You're trying to build something that someone is going to use, be it a doctor, a client, a patient, or you yourself. So, through this talk, I'm going to talk about those 4 processes. I'm going to focus mostly on setting the scene, because I think that's important. That's something that maybe you have not done enough or not in the same way at the university. Then I'm going to talk about how we get the data, but just briefly. And then I'm going to return to how you do the work, or how we try to do the work. And then I'm going to close up with some lessons learned. Now, obviously, what I'm going to be talking about is the lessons I've learned from working in the industry. So this is all motivated by actual projects we have done. Right, so let's get going. One term you're going to see in the industry a lot, it's been thrown around in software engineering mostly, but we're also making use of it here, is a so-called requirements engineering. Right, so what is your job as an AI researcher at a company like I am doing digital health? You have to deliver research outcomes to somebody. You have to give somebody models that do something. We'll see what that is later, or you have to find scientific insights. But you also have to ensure that results are valid. We're going to talk about those 2 particular problems. There's problems that you might face that might jeopardize your findings, and you have to take care of those. The problems that we have most worked on are largely of 3 categories. So one is what I call prediction. Does the subject have condition A? Yes or no? Do they have Parkinson's? Do they have Alzheimer's? Do they have COVID? Or how high would they rate on a scale? If they have depression, how high are they rating on depression, and so on. The other more interesting kind of problem is you have to monitor their state over time. If they're having COVID, are their symptoms getting better or worse? If they're having depression and you give them an antidepressant, are they getting better or worse? Should I, as a doctor using your system, should I do something? Is an intervention needed on my side? Should the patient go to the hospital? Those are things you have to think about, and those are things that people want to see from your system. And the other one is what I call deriving insights. And this is especially tied to the last part about interventions. A doctor might do something to somebody. That's why you go to the doctor. So they do stuff to you. And they want to see what effect did this have on the subject's voice in this case, since we're looking at voice, but overall on the subject as a whole. This is what the picture looks like of requirements engineering. This is also a process, and I'm assuming there's 2 parties here. There's you as an audio expert, or an audio and medical expert, and the medical expert that doesn't know anything about audio, basically. I'll talk more about that later and problems we have, because medical experts might not be aware of problems you have in the audio domain, so it's your job to explain those problems to them. So you set the audio requirements, you guide them to collect data under your requirements, and you validate it. You have to validate that they collected the data rightly. And what they have to do is help you define the problem, and of course help you gather the data and so on. So it's an iterative process, and this is where people outside your team are coming into play. You have to communicate with clients that might not be understanding exactly what you're doing, and it is your job to communicate exactly what you're doing. Otherwise, you're going to have problems later on. I have an example of that later. So let's move into the problems we're solving. I talked about prediction. I'm assuming most of you are aware of that. You're trying to predict a state in a what I call a static scenario. So the static scenario is the standard IID, independent and identically distributed assumption. You get samples, voice data, and you get associated labels. And then your goal is to learn something from that, either build a model that predicts Y from X, or learn some association between X and Y. This translates to what I like to call, patient goes to a doctor's office once, and the doctor just checks if they're sick. They're saying yes or no, they are or they're not. Some examples of that in real life. Björn talked before about the COVID-19 work we're doing. So another simplification of that is you collect coughing samples from people, you get labels, you get a PCR test or whatever, and you're saying, whether they have COVID or not. So you're building a system that classifies whether they have COVID or not, given a coughing sample. Same with speech samples for Alzheimer's, depression, Parkinson's. You can check their breathing. You can check their heart rate. So these are things where you have the data and you have the labels, and they're both happening at the same time under the IID assumption. There's a different formulation. There's what I call the forecasting problem in this talk. This is happening in a dynamic scenario. So dynamic scenario corresponds, essentially alludes to the fact that you're having a time series problem. What you're having in digital health in general is patients. You have people. You're assuming that the people themselves are the patients, the observations you have from the patients themselves are independent. We'll talk about this later, but let's assume for now that you have different patients. Each patient has their own history, so to say. And so for each patient, you have codependent observations. So you basically have a set of audio recordings and you have a set of labels. I put them as two different sets, and you can see here that they use different numbers. And I'll talk more about that in a later part of the talk. But for now, you can assume that you have some samples of the speaker's voice and some labels associated with the speaker, perhaps at different points in time. So this already points us to the direction that this is a very hard problem. Now, why do we need to have a time series problem? I found an anecdote where not fun, but one of the earlier medical detection systems that was built in the 90s, they built rule-based systems, so quite old. But it turned out that the system learned the association that if we have asthma patients that are going into the ER for pneumonia, they actually have a lower risk of dying from pneumonia. This is very counterintuitive. We know that asthma patients that have pneumonia, they're actually in great danger. And what actually happened is that the doctors knew that, and of course, we're giving better attention to them. So they were receiving more intensive medical care, which led them to have better chances of survival. But if you were to use this system for triaging, this is the term when you go to the ER, too many people go to the ER, so the doctors have to choose who they treat, essentially. This is what's triaging. And if you use the system, then it was going to throw all the asthma patients out because it was going to assume, rightfully based on the data, that they have a lower risk. And this is obviously wrong. So this is one argument. We're going to see more as we go through the talk, why you need to care about past history and why you need to treat your problem as a time series problem. This translates to people walk into the doctor's office and something happens. So let's look at what's happening. You can still have your standard prediction problem, right? You can still predict y, which is your arbitrary label, at time t, given all the previous observations, voice observations, and maybe even all the previous labels you have up until that point. So that is one thing. So you go to the ER, your doctor looks at your history and they're saying, do you have condition X or not? The other thing they're interested in, and this is perhaps most important, is what is going to happen to your state in the future. Are you likely to fall sick again? If they admit you to the hospital, will you get better or worse? If they don't admit you to the hospital, will you get better or worse? These are questions that the doctors are facing, and these are questions that they want you to help them answer. Another question, a different way to view this problem is, should the doctor see the patient ever again? You might have gone to a doctor at some point, and at some point they tell you you're fine, you don't need to come to my office again. You're treated or your problem has gone away. And this decision basically corresponds to saying I predict or I estimate that at time tau in the future you are or not going to fall sick again. So this is also something you can do if you treat a digital health problem as a time series problem, right? And what you're doing is you're essentially constructing a distribution of a t that conforms to a set of constraints over your labels and your data at a future point. So you're saying, I want to find the maximum t until or tau until the patient has to come back to the hospital, for example. And to do that, I'm going to use observations, voice tests, and or other measurements. We'll see more about that later. What are examples of that, of those things I showed before? First thing is, what is my depression level, for example, at this state? The future looks something like, what is the prognosis for the cancer you're having? Doctors have to do that a lot in their day-to-day job. And what they're trying to do is, what they're mainly interested in is saying, what is going to happen to you in the future? And especially what's going to happen if I do think A versus think B. That's the doctor's job. And that's what you have to help them do. The other thing that's very important in today's world is, when should somebody do a PCR test? If you're, Florian's going to talk about tomorrow about what we're doing on the COVID space more thoroughly. But essentially, we know that the source of truth is a PCR test for whether you have COVID or not. But PCR tests are used to be expensive. So when should you send patients to do a PCR test? And when should you say, well, you're fine, you don't need to do one? That's a question you have to answer. This brings us to the problem of stationarity. This is an important problem in time series prediction and time series analysis, because you want to see if the thing that you're measuring is staying constant or is unaffected by the time period in which you're measuring it. There's strict sense stationarity and weak sense stationarity. I would dare say that the problems we're facing in digital health, they're not stationary. If you look at Parkinson's patients, unfortunately, they're getting worse over time. So as time goes by, they lose more and more of their motor control. If you look at COVID-19, the disease itself changes. We're having all those mutations right now that are posing problems all over the world. If you look at AIDS, cognitive abilities decline more and more as you get older. Doctors do stuff, and that changes the distribution. Pandemics come and go, and that changes the distribution itself. So, I would dare say that the problems we're facing are not stationary, and this is something you have to account for. We'll see a bit more on that later, how you can try to account for it. And a final note on the IID assumptions I mentioned before. I said, patients are independent, and in the digital health space for voice, we're treating them as independent. But if you look at what people are doing now for COVID-19, is they're saying they're not independent, and they're not. Patients transmit diseases to one another. If you have diseases that can be transmitted like COVID, you can have outbreaks, pandemics. And this is what actually the question there is, to see whether you're having an outbreak or not. If you look at what's going on in different places in the world right now, you're trying to figure out if you're having an outbreak of COVID, and should you go to lockdown or out of lockdown, and so on. These are important questions. And these questions are actually violating the IID assumption, because you're saying you actually want to construct a tree of dependencies between patients. You want to track the history, for example, who contracted COVID from whom, so on. And it's also not identical. You see patients now, again, talking about COVID, some patients have the long COVID syndrome, or what's been called as a long COVID syndrome, but some don't. Why? And some patients develop antibodies, some don't. Again, why? These are important questions, and these are questions that you can try to answer in your research, because these are the questions that doctors are interested in. And this is, if you look at the IID equation we had before, you're just putting a diagonal line here. You're saying these observations are not independent. They're not identically distributed. And this is a problem you're facing in the real world. Right, the last part I talked about, I'm not going to talk about this a lot, is insights. A lot of times people come to us and they want to have those insights, and the conversation goes like this. What does X do to patient A? Now, X is a disease, or X is more likely an intervention. This translates to people go into the doctor's office and they examine them and they prescribe a treatment. What happens? This is particularly important if you want to work at the industry. Chances are you're going to be working either directly for a big company or collaborating with a big company, and they're doing drug development. As they're testing new drugs, they want to see what the impacts of those drugs are to patients. They want quantitative measures, but they might also want, in some cases, qualitative measures. They might want to see, if I create a new antidepressant, what does it do to patients qualitatively? Because that helps them understand what their drug is doing. So this is an important part that clients are asking more and more. This goes back to causality. This is an emerging field, or has been an emerging field for many years now in AI. I encourage you to look at it. What you're basically saying is that changes in the voice data are caused by other variables. The disease itself, you're assuming, since you're studying it, that it has an effect on the voice. So this is the voice, this is the disease. There's also other factors that are having an impact on voice. Emotion is one of them, age, gender, whatever. Several factors that have an effect on voice may or may not have an effect on voice. There's an effect of the disease in those factors. And then that's what people are interested in, is the intervention. I prescribe medicine. I do a surgery on a patient. What effect is that going to have on the disease? That's what they want to measure. They want to treat or cure the disease. So they want to make it go away. But unfortunately, this intervention might also have effect on the voice. And it might also have effect on the other factors. And it's your job to help doctors understand what effect it has on the voice itself, and perhaps most importantly, what effect it has on the other factors. So look at a small case study, right? As I said, you're evaluating a newly developed drug. So you're doing your test to get medical certification, for example. So you're measuring your subject baseline, you get a history and so on, and then you start giving a test group and a control group. You start giving a drug to some and a placebo to the others, and so on. Standard medical trial. What do you want to see eventually is you want to see if there's changes in the disease levels. That's what the drug is about. But what you also want to measure is, does it have unwanted side effects? Side effects that may or may not be measurable through speech are they having sleep problems? Are they having breathing problems? Are they having mood changes and so on? These are things that have to be measured and reported. And if you can do that, then you're bringing a lot of value to the partners that you're doing, or you're a company that's doing this medical trial. So while doing those things, you might encounter the following pitfalls. The first pitfall you might encounter, and we actually had a version of that in project, is how do you define what I call negative space. For example, think again about COVID, right? You want to see if a person has COVID. But what is your negative class? Is it just healthy people, or is it also people that are having the flu? This corresponds to differential diagnosis, I think, is a medical term for it. So what are the alternatives to what you're trying to measure? And should you account for those alternatives? I think, yes, it's very important, because if you say that whoever has a stuffy nose has COVID, then this system is not very useful, because people that have influenza also have COVID, but we're treating it differently at this stage in time. So when you're constructing your classification problem, for example, it really matters what you put in the no here. Yes is simple. You take all your COVID patients, you say they have COVID, you put them in yes, that's your positive class, that's fine. What do you put in your negative class? If you put healthy 20-year-olds in the negative class, it's going to be a very easy problem, but the model you're going to build is not going to work in the real world. If you're treating Alzheimer's, you're going to put Alzheimer's patients in yes. But if you take college students to be your control group because you have easy access to them and you put them at no, then you're building an age detector, and it's a pretty easy problem to solve. But if you actually start testing this detection model in people that are in the 60s and 70s, it's always going to show, most likely going to show that they do have Alzheimer's, even though they don't. And that's because you constructed your negative space in the wrong way. And so on. So this is a very important problem. And this is part of setting the scene. You know, you have to define that beforehand in collaboration with the medical experts, of course. And if you don't do it right, you risk having invalid results. So yeah, it's defined by the experts. They tell you what are conditions that you have to take into account, but what you also have to do as a speech expert or as an audio expert, you can help them define states that are measurable or you know that have an effect on sleep. But the experts might not think about it. So thinking about cognitive abilities, you know, age-related cognitive decline, I think is the term for it. A medical expert will tell you that they want to benchmark this against patients with dementia, patients with Alzheimer's, patients with Parkinson's, whatever. And patients that are all in the same age group, starting from 60 and onwards, for example. They might tell you that. And you can set up a suite of voice tests to test for that. But when you do your voice test, you know that there's other things that are affecting speech. So, you know, is the subject tired? Are they stressed? Are they sleepy? Are they perhaps intoxicated when they're having the test? Those things, if you can measure them, and we can measure a lot of them quite well from speech. Those go back to the compare challenges that Björn talked about in the beginning. You know, these are part of your negative space. And why are they part of your negative space? Because ultimately, as we see later, the voice tests are administered at home. They're not administered by a medic, or they're not always administered by a medical professional in the lab. So they don't have control over those factors. And so you have to measure those in the wild. Next is what's called the clever Hans problems. Clever Hans was a horse in Germany last century, and he was purported to answer mathematical questions. So people would ask him questions like 2 times 12 equals what? And Clever Hans would tap his hoof on the ground and answer the question. And he used to answer a lot of those questions rightly. Now, of course, this didn't make sense. You know, you had a mathematical genius as a horse, and people looked into it. And what Hans was doing is he didn't actually understand the question or know how to count, but he could sense what people were expecting of him. So as he was tapping his hoof and getting closer to the actual number, people's anticipation would rise. You know, and as he got to the exact number, you know, people would be waiting to see, will he get it right or not this time? They had a lot of emotional arousal, and he could detect that, apparently, or that's the hypothesis, and thus he knew how to stop. And they did some experiments to measure that hypothesis. Now, there is evidence that machine learning problems suffer from the same, machine learning algorithms can suffer from the same problem. One notorious case is this, again with horses. You had this well-known data set, image recognition data set, and you had one of the classes was horses. And some of the pictures were taken by the same artist. He was doing pictures of horses. He was always putting his watermark on them. So what some systems learned is to identify the watermark. You can see that by those heat maps that attribute the importance of its pixel to the final decision. And if you remove that watermark, you're not getting the correct decision. And there's other examples, you know, airplanes identified by the blue sky, wolves versus dog by the snow, and so on and so on. You can find tons of examples of them. So what are clever Hans problems, actually? They're primarily caused by data. So let's go back to the diagram, to the simple diagram we had before. You know, you have X, it's affected, it's caused by Y. The disease is causing changes to X, but other things cause changes to X. You know, in medical studies, you're taking great care to stratify your data based on age, sex, race, so that you don't unintentionally introduce confounders in your data. So what you're observing actually is X, given both Y and C. Right? Those things happen at the same time. What you want to do is you want to measure or model Y so, infer this relationship, y from x, independent of c. So you don't care about this. You want a model that can correctly identify y, regardless of what this is. Now, the clever hands problem is the worst case scenario is here. So you have samples x, y, and c, and the clever hands problem corresponds to the fact that whenever you have a label y, so whenever your disease is true or false, so you have one condition. So one condition for true, one condition for false. And in this case, you cannot tell apart if it's the disease that's causing the changes or the conditions that are causing the changes. This is why medical experts take care to stratify those things in the studies. So they have gender balance, age balance, race balance, and so on. But there's also clever hands problems in audio. And this is a real tale from working in the industry. At some point, a client approaches to identify condition. It was a binary, yes or no. Do people have this condition or not? They had already recorded subjects, so they had the data. They just gave us the data, and they told us, do your machine learning stuff. We did our stuff, and we got very good accuracy. But as we looked into it more, we got suspiciously good accuracy. And what we found out, after a lot of effort, was that they had recorded all subjects with the condition A in one room, and all subjects without the condition in another room. And to make matters worse, one room was a normal room, so it had some acoustic treatment. The other apparently had no acoustic treatment. So it had a lot of reverb. Now, reverb has a big effect on the audio signal. And this is what was giving us the higher accuracy. And so there was no way at this stage, there was no way for us to go back. You can do reverberation, but these algorithms are not perfect themselves. So we're still going to leave artifacts in them and so on. So, we had to forego the study and ask the client to go back in the lab and collect more data in better conditions. So, and this makes sense because they were medical experts. They did not know that different rooms might have an effect on the signal, and that you have to keep your recording conditions the same. It was our job to tell them, and we did after we got the opportunity. But this was a case where they had the data, so we didn't have a chance to do the setting the scene part beforehand. So if you have, or whenever you have the opportunity to set the scene, make sure to take care of those things. Speaking of data, how do we get it? There's different ways. I'm going to be briefly talking about that because I think Florian's going to be talking more about it tomorrow. Basically, you need access to subjects, right? You need access to patients. You can get them through medical professionals. You can collaborate with doctors, hospitals, and so on, clinics. You can get them through a client, like we've done in a few cases, as I mentioned before, or you can build your own app. This is what Florian is going to be talking about tomorrow, AI Sound Lab, which is what we're building at Adhering. These are all great ways. I'm not going to say one is better than the other, but you have to control for those factors we talked about before. And how you control them is different in each case. If you're getting the data through medical professionals, you have to somehow train them to avoid those clever hands problems. At least the clever hands problems caused by audio, the others are their job, I guess. If not, you have to scale up your data collection so that these clever hands problem disappears. If you have data from people in different recording conditions, then the recording conditions are not going to be a confounder. The problem is when you have few people in very specific conditions and conditions associated with one state or another. So, when you think about getting the data, you have to think about those things and you have to design your data collection protocol accordingly. One thing that's coming up more and more, and if you start working in this industry, you're going to see this is a big factor, is privacy, GDPR compliance and all that. You have to keep the identity of the subjects hidden. So, some lessons learned from the industry is that you might never get access to the raw audio files, for example. We've worked with clients who have data, but they're not allowed to share them with us. How do you get features then out, and how do you conduct your analysis in those features? You know, we're using OpenSmile a lot. Florian's going to be talking about that. You can also use, you know, other things, but you're basically not allowed to get invertible features. So you have to do something to anonymize the data, but still keep all the information you need to solve your problem. That's a big concern, obviously, nowadays. This brings us also to quality control. You know, if you get your data, how do you check post hoc if your assumptions hold? How do you deal with noisy data, for example? How do you deal with noisy labels? How do you figure out if you have noisy data? How do you figure out if you have noisy data if all you have is features and not raw WAV files that you can listen to? Missing data, we're going to talk about that later. You know, these are things, these are part of the data science work that you're going to be doing in industry, and they're not easy at all to do. I'm going to sketch the solution we're using. You know, quality control, you can do anomaly detection, but by itself, it's not enough, because often what you're looking for is anomalies themselves. So, you know, you're collecting data for people crowdsourcing like we're doing for COVID, and most people do not have COVID. So, you know, COVID itself is an anomaly. I mean, certain percentage of people get it. It's 1%, 3%, whatever of your data is going to have that condition. So if you look for anomalies, you know, chances are the anomaly you're going to find is what you were supposed to be looking for anyway. So it's very hard to look for anomalies and find the right things. Manual auditing, you know, it's expensive. You have to hire annotators to do it. It might not be possible if you don't have the audio files. And it's also error prone because, you know, people are quite good at integrating those conditions away. People don't care if you recorded in room A or room B. That's why the experts themselves did not see the problem. So, you know, it's very hard to train annotators to do that job and to understand what the problems are for machine learning methods or audio analysis methods. So what we've settled on is these iterative human-in-the-loop approaches. So you do some kind of automatic auditing, you collect data, but then you send them to annotators so that they can verify whether the data is correct or not. So this is what I recommend at this stage in time, that you set something like this up. So you got your data, and now let's go to the part where you're doing the work, fun part. Let's talk about prediction problem first. So building a model is the easy part, assuming that you got your data and all that. Well, it's not easy, but I'm assuming most of you guys know how to do that, so I don't want to talk much about it. You build a classification or regression model on your data. You know, you use all the standard tricks from the we know are working from the AI domain. You know, transfer learning, fusion learning. You got to have your algorithms ready for that. You got to pick your metrics right. This is done actually during problem definition. You care more about sensitivity or specificity. You have to be sure what you're trying to optimize. But I'm assuming that all of you guys know how to build a model. So let's look at it from an industry perspective, though. You know, building a model on some data is not enough. There's a few other steps that you have to do. The first one we're doing at Adhering is what we call stress tests. So you have your data set, you build your model, you get X% accuracy or whatever metric you're measuring on the test set. It's fine. What do you do then? Well, you're trying to understand basically if you build the right model, if it correctly models the problem you're trying to solve. You know, this goes back to was your data representative and all that. But, you know, how do you measure that? One thing we're looking at is how does a model behave across different user groups? You know, the so-called fairness analysis that's gaining steam in the machine learning community. Oftentimes, you don't have labels for this. So you don't have simultaneous labels for all the groups that you're trying to measure. So you might not have labels for people of all different races and all different genders, for example, and all different age groups. You might have to source the data from somewhere else, and you might have to test the behavior of your algorithm on unlabeled data. And from that, try to infer, you know, what is its behavior on the actual data, on the actual population you're going to deploy the model on. This is a hard problem, but this is how we're dealing with it at the moment. You know, did it pick up spurious correlations? For that, we're doing post hoc analysis. You're trying to look at, again, going back to how the model behaves when you run it on data. You can run it through biased data and see how it performs when the data itself is biased. Does it react to those biases, so to say? Finally, how does it handle the different acoustic conditions? Depending on how your model is going to be deployed, you're going to make sure it's going to be working irrespective of the acoustic conditions, different rooms, different microphones, so on. For that, we're doing robustness analysis. So we're essentially running it. We're simulating those conditions, starting from clean data, and then we're testing how it performs in noisy data or corrupted data or transformed data, however you're going to call it. This is also something very important. When people ask you to build a voice test, they're assuming it's going to be working, especially if they're doctors. They're assuming that they can take out their mobile phone, record a segment, and it's just going to work. Because as we know from speech processing domain, it's very challenging. And it's very important that you have measured that before the doctors actually start doing it, so you know in advance of whether it's going to work or not. And finally, you test your model and you put it out in a production environment. Are you done? No, you're not done. You have to make sure that it's working, that it keeps working. One thing is, how do you incorporate user feedback? You might give it to a client, a doctor. They might test it with their patients, and they might just come back to you and tell you it's not working. What do you do then? How do you use that information? You don't have data, you don't have labels, you just have anecdotes that the model is not working. How do you move from those anecdotes to something that you can actually make use of? How do you collect data? For example, you can make your app collect data, and then you can try to get labels, and you can use it. Does it perform consistently well over time? Does it? There's this thing that model performance might degrade over time. Well, the model is not changing, obviously. What's changing is the world around it. If you had a model that's predicting respiratory diseases before COVID, well, the world changed after COVID. So your model is not going to perform just as well. Basically, what it's doing is seeing out of distribution examples where can you detect that? Can you detect that in time? And can you do something about it? This is very important. You have to take that into account when you're building a model that's going to be used in the real world. You have to think about beforehand how you're going to measure how that model is doing in the real world. And what you also have to think about is, because the answer to those questions is going to be that the model needs improvement, is you're going to have to think in advance of how you can set your model to improve over time. So can you learn from data without labels, for example? Well, one way to do those things is, and again, that's why I like forecasting problems, that they give you ways to accommodate all those things. So let's look again at the forecasting problem in the wild, what I talked about before. You have voice tests. I keep talking about voice tests. What are those? They're what I call recording sessions. You ask a person to do a voice test. They go to the lab, they record some segments, different segments, and so on. Then how do you know their state at this point, where you need clinical evaluations as you're building your data set, or even as a system is deployed? At some point in time, they're going to go to the doctor and they're going to get an evaluation. And this you can consider more or less ground truth, sometimes more, sometimes less, depending on the condition. Put them outside. So the fact is that they might not be concurrent. They might not be happening at the same time, because if you think about the broader picture, what doctors want is a voice test that you can basically do at home. They when you go to the doctor's office, they do your blood test or whatever test they're doing. They know what to do with you. They know how to measure your condition. Essentially, what they want from you is to measure their condition, measure the patient's condition when the patient is not at their office. So the voice tests are not going to be happening at the same time you're getting your medical evaluation. They're going to be happening at a different time. And in fact, both things are going to be happening at different frequencies. If you think about how often you go to your doctor's office, you might be going once a month, once every 2 months, 3 months, 6 months, 1 year. But voice tests are free. You do them. The idea is to do them at home with your mobile phone, your computer, or whatever, and you can do them weekly, daily, hourly, whatever you decide. So the fact is that you're going to have different frequency rates, sampling rates. Moreover, as I said, voice test is a single session, but a session is made of different things, smaller segments. They could be VAD segments. So, as I'm talking right now, if this was not a presentation, but a voice test, you would be cutting my audio using VAD, voice activity detection. You would be analyzing its segment differently. But often what you have is targeted voice tests. Again, as Florian's going to show tomorrow with AI Sound Lab, we have different tests in it, a battery of tests, basically. You go to the doctor, they ask you to say, ah. They ask you to cough, to breathe, to do different things. There's different things that you're doing. Are those things measuring the same thing? No, they're not. If you look at COVID, for example, what we did is we're asking people to produce nasal consonants, and and when we're trying to measure that is if they're having a stuffy nose, so to say. That's different. That's measuring a different thing from the I. The I is measuring one thing, the M is measuring another thing. How do you combine information with those things? A cough measures another thing again. So you might have to build different systems for them. You might have to build a model that's working on cough versus a model that's working on O's versus a model that's working on the consonants versus a model that's working on real speech and so on. And then you have to combine in the predictions of all those models, basically. We talked about the asynchronicity problem. So, why are voice tests and sessions asynchronous? Well, as I said, why would they be? You're not interested to test the person when they're at your office. You're interested to test them at home, because what you're doing is you're examining them, and you as I said, you're prescribing a treatment. You're doing something as a doctor, and you tell them, they should come back at your office in 6 months' time for a reevaluation. Well, you want to obviously you're asking them to come for a reevaluation because their state might have changed. And so what you want to do is you want to use your voice tests to measure how their state is changing between the first evaluation and the second evaluation. This is also alluding to the misalignment problem. So as I said, voice tests are way more frequent than the clinical evaluations. So you have the baseline evaluation, you go to your doctor, they tell you have condition X, that they have to monitor you and so on, and they tell you to come back at time Y. And in between, you have a lot of sessions, a lot of recording sessions where the doctor is getting the data. Okay, that's cool. But how do you, as a person who's developing these models, this is the data you get at the end of the day. If you conduct a study, this is what you're going to get. You're going to get weekly, for example, weekly voice tests and bi-monthly evaluations, for example. So the labels and the recordings are going to be misaligned. And that creates a problem when you're building your model and conducting your analysis is how do you get the labels for those sessions? The sessions measured something, but how do you know what they measured? And that is a problem we're dealing with right now in one of our projects. You can go with the so-called homeostasis hypothesis. You can say, person's state, well, it doesn't change so much. If they have the condition at time t, they have the condition time t plus 1, most likely. But that is only true for some time. And this some, you either have to get it from the experts if they know it, or you can try to learn it. For example, if you think about cancer patients, right? They have a cancer at time 0, and they do their evaluation after 6 months. Well, they're doing the evaluation because their tumor might change. And so, it's reasonable to say that 1 week after the first evaluation, the tumor was the same, maybe 2 weeks, maybe 3 weeks. But after some point, it's not reasonable anymore to say that the that the tumor has not changed. That's why you're doing those evaluations in the first place, because you're assuming that things are changing. And so this is creating a problem when you have your data, if you get data like that, because it's quite often that we do get data like that in practice. This is not a hypothetical example. As I said, you know, how do you then, what do you do with that data, basically? What do you do then with missing data? That's also another problem. What do you simply, you know, you have a database, and you know that people are doing weekly evaluations, weekly voice tests, or clinical evaluations, and you know the frequency rates of those things. What if you find data that is missing? Do you simply remove those entries from a data set? Well, that may not be a smart thing to do, because assume that you're measuring people with depression, right? And they're doing weekly voice tests. What if they miss a weekly evaluation? Does it mean something about their depression levels? Maybe they missed it because they're relapsing, they're having it really hard, and this is actually an alarm situation, and you have to call their parents or their doctor or whatever so that they intervene. What if they miss a monthly evaluation? Is it because they're getting better or worse? This depends on your problem, because, you know, scenario B, patient goes to the hospital, they may or may not do some test. Well, the fact that they may or may not do a test means something. You know, doctors decide based on the clinical image if a test is warranted or not. So missing data is not something in the digital health domain that you can simply discard and say, I don't care about it, I just remove it. You know, pandas drop now. You have to take it into account. There's different ways. One promising way is to incorporate into modeling. I point you to this study where they're looking at recurrent neural networks and think, to be exactly, use GRUs, and they actually modified the GRU equations to take into account potentially missing data, kind of slightly adjusting the homeostasis hypothesis we said before. Next is you're getting extra information. As I said, you know, you have your clinical evaluations, right? You have a voice test, but you might also have other measurements. You know, based on your voice test or based on the clinical evaluations, the medical experts might provision more tests. For example, blood tests or whatever. How do you take that information into account? And this information, by the way, arrives at different points, right? It might arrive in between a voice evaluation, might be just in time for a clinical evaluation. They're basically coming and going whenever the doctor decides. Can your system handle that? Can you say, you know, I'm using that information. What does an information do? Maybe you can take it into account as an extra input to your model, or maybe it changes the prior probability. You know, if you have a very accurate test here that's saying, you know, the tumor is growing, then this changes your prior probability at this point. So then, as you model, as your time series progresses, you know, since session 2 now is going to have a different prior probability from session 1, since you had an extra measurement, you know, it's going to give you a different output, for example, a Bayesian way. That's a Bayesian approach to it, and so on. But this is something you have to, if you can. I mean, this is optional. You can skip it, kind of, but it's very, very useful to use it. So I encourage you to try and think about how to use it. Finally, we're going to a more complete picture. You know, if those things I'm talking about are not problems, you know, as I said, forecasting gives us a way out of the problems we're having in prediction, actually. We're getting, one way to view those things is as sparse rewards. You know, you're saying rewards in the sense that you're modeling your problem, you're constructing a model of the world, and at some point you get something that you consider close to ground truth that's telling you whether you're right or wrong. That's a terrific learning opportunity. That's more human-like way of learning, and it's of course leading to reinforcement learning work. And potentially it's a great opportunity for us in the audio domain to finally start looking into reinforcement learning approaches, where we're saying, I'm using the voice tests to learn something, and then at some point I'm getting a label from the expert, and I'm incorporating that knowledge to make my model better. I'm trying. This is a kind of a system that's constantly moving towards a system even after it's deployed in production. It's kind of constantly learning. You might want, for example, if you think about how do you predict or how do you tell a patient when to go to the doctor, it's a very hard problem. But one way to do it is when you have that observation, why, basically the patient should have gone to the doctor at this point if their state has changed, right? If the state is the same as here, then they don't need to go to the doctor because their state has not changed. What is true before is true now. Basically, why people go to the doctor is to see, am I getting better or worse? Now, your job with a voice test is to tell that, and this is your information. So if you have a model, it's predicting based on session 1 and session 2. Should the doctor go there? Well, it's basically predicting, has the state changed, right? Is state here different than patient state here? And after a while, you do get an answer. You have your clinical evaluation, so that's giving you a reward. It's a sparse reward in the sense that you have a lot of sessions here. You might have 10. And using those 10 sessions, you're predicting what's happening here, and then you get your reward. So, this is one way to start thinking about this as a reinforcement learning problem and benefit from that instead of seeing it as a challenge. Right, one final word on integration. This is basically a systems approach to digital health, right? This is a biggest difference to the in the lab conditions, actually. In the lab conditions, you're building a model, you're deriving insights, you're done. You publish your paper, you're done. When you're building a model that's going to be used in the same work, you're having to do with people in the digital health space. You have to do with doctors and you have to do with patients. And what you're trying to do is you give information to both and get information from both, with the ultimate goal, at least in this stage in the digital health domain, to improve the communication between them, if you can see it in such a way. You want to provide more information basically to the doctor, but also to the patient about the patient's state. Moreover, the information that you provide has repercussions. So based on your information, the doctor will decide to either do or do not something. And this is going to change the state of the world, because it's going to potentially change the state of the patient. And what you actually want to do is you want to measure the change in the patient's state. So, you have to think of your model or whatever you're building as an interactive agent. It's an entity that's interacting with other entities, and its decisions have repercussions in the real world. This is a good time to circle back to that asthma, to that rule-based approach. We talked about in the very beginning about asthma patients having a lower risk of dying from pneumonia. If you were to use that system, and if doctors were to trust the system for whatever reason, then you would start seeing a huge spike in people that have asthma that are dying from pneumonia, because they actually do have a higher risk. It's only because doctors were already treating them for that risk that they exhibit a lower risk in the data. This is an example of, you have to think about and you have to measure what changes your system is causing in the world, especially as you start going into more deployment environments where doctors are actually using your tools to make decisions. These decisions, they always have an effect. That's what medicine is. You're doing things. You go to your doctor because you want them to do something to you. And so if your doctor consults your machine learning system, they're going to make a decision, any decision. And since it's informed by the system and it's going to have an effect on the world, you have to measure that effect and you have to take that into account. This is a very important problem, because otherwise your system is actually basically going to be kind of useless to the doctor. Right. So lessons learned. As I said, you're not building a model in a vacuum. You're not working with clean data, and you're not solving a static problem. You're not done after the model is built, and you're not building an quote AI, right? Whatever that means. You are, though, building an agent that interacts with the world, as we saw before. You're constantly validating your data. You're never done validating your data. You have to set up processes that continuously validate your data. You're not working on a static problem because you're chasing a moving target. Diseases change, patients change. Doctors do things to patients and cause them to change, and so on. You must be constantly evaluating your model because the environment is changing. And you're building a system that helps doctors and patients. You're not out there in the world yourself. So, conclusion, this work is fun. I hope I managed to get this across with my talk. You have to be prepared to bring a holistic approach because there's a lot of things you can bring to the table as an audio expert. You have to know your assumptions. And, I hope I convinced you that building medically certified, especially medically certified AI products is not a last mile problem. So I know that you guys are already experts. I think most of you are close to finishing your PhD studies, so you're close to getting your doctorate degrees and so on. Your life is not over. If you go to industry, you're going to face a lot of exciting problems. You're going to have a lot of fun trying to solve them. Yeah, it's exciting times lie ahead for medical AI. So thank you all. And do you have questions?
Thank you very much, Andreas, for your talk and the very interesting insights you shared with us. So, yes, are there any questions or shall I start? Okay, so I would be very interested to know who are the typical clients of Audeering. So are these medical doctors working in a hospital or, yeah?
So there's two kinds of clients. There is, how to put it, clients are right now, so to say, paying us money to do things for them. Those are mostly bigger companies. Unfortunately, I think I'm not allowed to mention all of them. So I cannot give names because that's one thing that you guys know. A lot of industry work has to remain confidential for some time until you publish your findings. But basically, we're talking about big pharmaceutical companies or also smaller companies that are trying to build a product. I have to say that that's because Audeering is mostly a technology provider. So we have voice technology and we're providing it to other companies so that they build products. What we are doing right now with AI Sound Lab is trying to go to the source, trying to develop a relationship with doctors that they can use AI Sound Lab to with their patients to derive findings. But basically, if you have to work with, mostly the way to get to patients is to work with big organizations. Big pharmaceutical companies, they are the ones who have access to patients. They have cohorts of patients testing the drugs and so on. So you have to work with them. And alternatively, though, I think we have not managed to do it yet, hospitals, but they're mostly also the way to get to them is through the big pharma companies.
Okay, I see. Yeah, thank you.
Yeah, welcome.
Further questions, please.
Okay, I'm very, thanks a lot for your interesting talk. I'm very interested in the subject-wise prediction. As you know, we normally do the subject-independent experiments. The data is from many subjects usually. So in such a case, if we want to create an agent to interact with the patients, so if I'm curious if it is necessary to have an initial model which is trained on the multi-subject datasets.
Yes, it is very important to start with a multi-subject dataset. It is also important to keep in my opinion, to keep the subject independence assumption when you split your data into training and testing. But what you can also do then is, for example, to assume what we have in some data sets at Adhering, working with some clients, is we have longitudinal data. So we have the same patient for several months, basically. What you can also do is you can take the first months of the patient, put that in your training set, and take the last months and put that in the test set, for example, so that you simulate their movement through time. So you can then train on all patients. Or what you can do is you still keep the speaker independence split, but you train a model that learns to start from the first months and go to the last months, and then you train it on some patients and you go to other patients. What you can also do for personalization, to answer your question more specifically, I think the best way to go is towards the direction. If you know a paper by Björn and Augie Rudovitz, if you know the work of Augie, for example. So what he did is he had a big model, a few shared layers that you share amongst all patients, and then personalized layers that are personalized to each patient. So you basically have a model that's, part of it is learning the bigger picture from many people, but it's also specializing to different patients. I think for digital health, this is very important.
Okay, thank you.
Welcome.
Are there further questions? Okay, then if not, thank you very much again, Andreas.
Yeah, welcome.
And we will now have a coffee break starting, actually now. And at 10:45, the early stage researchers will meet again here in this Zoom room. And they will have a discussion round, and Chao will guide you through this discussion. And then we will have a lunch break, and at 2 p.m. we will all meet here again in the Zoom room for the early stage researcher presentations. So then, Chao, I guess we can all leave the Zoom room for the moment. Is this right? Yeah.
Yeah, I think so.
Okay, and Chao sent another email with the Gather Town links for the virtual coffee breaks. So you can just click on these links and then you can join. Okay, see you later.
See you.